Welcome back for page 72 in the textbook. And I'm looking at example number 2 in the textbook, not the exercise. Jenny, David, and Lauren have tickets to a play and got 3 seats together in the same row. If each person randomly chooses a ticket, what is the probability that Lauren will sit next to David? So we're going to make a table of all the possible outcomes. So I'm going to draw a table. Let's do 6 rows and 3 columns. Okay. So we have 3 people. We'll make these be the seats. And so I'm going to say the first possibility, and these can happen in any order, we have Jenny, David, and Lauren. That's one possible outcome. Okay, another possible outcome would be Jenny, still in the first seat, and then Lauren and David. Okay. Then we could have David in the first seat, then Jenny, and then Lauren. Or we could have David in the first seat, and then Lauren, and then Jenny. Or we could have Lauren in the first seat, and then David, and then Jenny. Or Lauren in the first seat, Jenny in the next seat, and then David. So these are all the ways that we could arrange these seats. So how many different outcomes are there? How many rows did we come up with? There are 6 possible outcomes. And we've just listed them all right here. Here's 1, 2, 3, 4, 5, 6. So that is the denominator of my ratio. We want to know, if everybody chooses randomly, what is the probability that Lauren will be next to David? Okay, so we need to look at our outcomes. And here we have David and Lauren sitting side by side. Here we have David and Lauren sitting side by side. The order doesn't matter as long as they're sitting next to each other. Here we have Jenny and Lauren, or Lauren and Jenny. And then we have David and Lauren, or Lauren and Jenny. So we have 3 possible ways. That's not right, is it? Have I done something? I was thinking it would be 4. Let me look at the example. Yes, I've messed up somewhere. Jenny, David, and Lauren. Jenny, Lauren, and David. David, Jenny, and Lauren. David, Lauren, and Jenny. Oh, right there. Duh, Amanda. David and Lauren. I'm sorry, guys. I looked right over it. Okay, so it is 4. There are 4 situations where David and Lauren are sitting side by side. So our probability is 4 over 6. So we could say that probability is 4 over 6, which reduces down to 2/3, which is approximately 0.67, which is 67%. And actually, that is not approximately, that is 67. Okay, so there's a 2/3 chance, or a 4/6 chance, or a 67% chance that David and Lauren will end up sitting together in this scenario. So let me ask you this. What is the probability that they will not be sitting together? What is the complement of 67%? Well, to find a complement, in this case, you will say 100%, that's the certainty, minus the 67% is, what, 33? So the complement of 67 is 33%. Okay, let's look at another example. This was example 2. And you know what's coming up in example 3 if you're looking at the textbook. My very favorite thing in all the world. Tree diagrams. I hate them. All right, another way that you can count outcomes, we already have seen this, is to use tree diagrams. So here's the story. The clothes factory has extra large sweatshirts on sale. The sweatshirts come only in blue or green. Each sweatshirt comes with either a zipper or a hood. And each may or may not have a store logo printed on it. How many combinations of sweatshirts are available? Well, you go into the store and you say, I want to buy a sweatshirt. Okay, no problem there. Let's say I want to buy an extra large sweatshirt. So the first thing you have to choose is the color. You can choose blue or you can choose green. So if we were using the fundamental counting principle, which is my best friend, we would have color as our first variable, and there are 2 choices for color. And then you have to choose zipper or hood. So I'm just going to put zipper or hood. There are 2 options. So for the blue sweatshirt, you can choose blue with a zipper or blue with a hood, green with a zipper, green with a hood. Okay. What is 2 times 2? 4. So we have 4 branches at this stage of the game. Originally, we just had the 2. Now we have 4. Then once you choose zipper or hood, you have to choose logo or no logo. So logo or no, logo or no, logo or no, logo or no. So for logo, there are 2 possible outcomes. It either has it or it doesn't. So we're just going to say logo, no, logo, no. Okay, so now we have 2 times 2 times 2. That is a total of 8 branches. And then finally, what's the other? Oh, that was it. Okay. So, how many combinations are available? There are 8. We can see that with the tree, or we can see that with the counting principle up here, that we end up with 8 combinations. And let's see, they give us an example, so help me out here. What is the probability that you will choose at random a sweatshirt that has a hood? Okay, so draw out your ratio. Remember, the bottom is total outcomes, and we just found that. That's 8 possible outcomes. So we know that's going to be 8. And then whatever's in these parentheses will go up here. So how many of the sweatshirts have a hood? So let's come back up here and count. We have this one and this one. But remember, those go with these. So there are 4 possibilities with a hood. Let me do it this way because that's misleading right there. You're looking at a blue hooded sweatshirt with a logo, a blue hooded sweatshirt with no logo, a green hooded shirt with logo, and a green hooded with no logo. So there are 4 possibilities with a hood. That is 1/2, or 0.5, or 50%. Okay? There is a 50% chance that you will choose one at random, that's with your eyes closed, that has a hood. And while I'm thinking about this, I want to give you something to memorize. I rarely ask you to memorize because I believe that the best way is to understand what you're doing instead of trying to memorize everything, because you just can't memorize everything. But this is something that's worth memorizing. So let's draw a table with 3 columns. And in the first column, I'm going to put the fraction, the decimal, and the percent. When I was a little girl, I followed my dad everywhere. Everywhere he went, I went. And he had a workshop with this chart on it that looks very much like this. So by the time I was 5 or 6 years old, I had memorized a lot of decimal equivalents. And that has served me well through my life. In fact, when I was learning to do fractions, I could convert them in my head to decimals, do the math, and then convert them back to fractions. And my mom thought that I was cheating on my homework when I came home with fractions homework. Then she realized what I was doing and she made me learn the fractions. And I'm glad she did because I needed to know that. But okay, let's put the decimal and fractions in here. So the fraction 0, which is not a legitimate fraction, you cannot have 0 on the bottom of a fraction. That is against mathematic rules. So let's fix that. I don't want you to think that's okay. There really is no fraction here. But the decimal would be 0% or 0.0. So 0%. 1/4, the decimal is 0.25. What is 1/4 of a dollar? It's a quarter, 25 cents. That is also 25%. 1/3, the decimal is 0.33, that repeats forever. So the percentage is about 33%. 1/2, half of a dollar is 50 cents. That's 50%. 2/3 is going to be 0.66 repeating. So we're going to say about 67%. That one will round up because of this third 6 out here. Then 3/4, that's 3/4, 75 cents, or 75%. And then 1/1, that's 1 whole, or 100%. Now you can also do 1/10, 1/20, 1/5. You can do any of them. But these are the ones that I would memorize, because these are the ones that are going to come up very often in life. And they're just good to know. Those of you who may work in construction, you probably already know your fraction decimal equivalents. So use that knowledge. Use whatever you have to do these problems. All right, we are to the end of page 72, and I'll see you back for page 73.